Now audio is where?
Audio is here.
Where's the Zoom? Yeah. Okay. Yeah, so hello, hi Mark. Hello.
Hello, Priya. Good afternoon.
Hello.
Can you hear me?
I can't hear you. I
Oh,
can't
you
hear
can't
you.
hear me. Okay, let me
Because
try and
the
sort
audio
that
nahi
out.
मैं बंद किया था शायद.
Just 1 minute, put on the audio. Yeah. Can you speak again, Mark?
Yeah, can you hear me now? Can you hear me now? No, you can't hear me? I have this problem.
The same as system. Yours is showing some other
That's right. That's
speakers.
correct. वो सब सही है.
Wait, 1 minute, 1 minute. We'll try. This is saying RPG series.
ये वो सही है. High definition.
This one,
ये वो सही है.
personalized.
यहाँ पर भी नहीं आ रहा है.
Just check.
Okay, you still can't hear me?
Can you try speaking? Can you hear me? You
Yeah,
can hear me?
I can hear you,
hear
but
me.
you can't
Great.
you can't hear
You
me.
can't hear me. Okay.
I can.
You can hear me. You can hear
Yes.
me. Great. But I can't hear you.
Okay.
1 minute.
Let me try to sort it
Okay.
out.
1 minute. We'll just check the audio settings. Maybe this.
Can you hear me now? Nope.
Okay, just speaking again.
Yeah. Can you hear me? Can you?
Yes.
Oh, you can hear me?
Yes.
Oh, very
Yes.
good. Okay, excellent.
Najam, now it's come. I changed the speaker. Okay. So, okay. So, 1 minute. We've got. Yeah.
Right.
Yeah.
Okay.
Great.
Good.
Okay. Yeah. So welcome, Mark. We have Mark Taylor with us next, who's going to talk to us about TOPCAT. And I think you can start, or you want to wait for some time, or you're ready?
I can start if people are here.
Yeah, great. Yeah. So the stage is yours.
Thank you very much. Let me just check I can share my screen.
1 minute. I just need to play a little bit the audio. Just 2 minutes.
Okay.
Still coming a little soft. But Cheng Sui came so good yesterday.
Because that was from here. No?
Well, it could be at my end. Is that any better? Is that any better?
1 minute. But just, it's a little better, but not good for everyone. No?
Okay.
Great. Now,
Okay, I'm speaking. Is that any good?
Just give me 2. My audio on. Let it play. It's a little louder. I do this.
Mic.
Yeah, Mark, can you just speak again?
Yeah. Can you hear me? I'm speaking. 1, 2, 3, 4. Is it still too quiet?
Can you say something, Mark?
Yep. Is that okay?
This is good.
Can you hear me? Can you hear me?
Now we are good.
Okay.
Mark. Yeah, so I've done it from here. Okay, now it's perfect.
Okay, that's ready to go. I can't hear I can hear an echo at the moment.
Yeah, it's good.
But I think
It's
if you
good.
turn off your microphone, it'll be okay.
Yeah, I'll do.
Okay, that's good. There's no echo. Okay. Right. So, shall I start? I'll start. Right. Thank you very much, Priya, for inviting me. Hang on, let me get rid of this header thing. All right, I think it's better. Right, so thanks very much for inviting me. Priya asked me to give a talk about TOPCAT. And she said not to do the sort of normal introductory one, do something a bit more advanced and with some more recent features in it. So that's what I'm going to try and do. So what I won't do is introduce TOPCAT from the ground up and say, this is what it does and this is all the features. I'll sort of plunge in. And the format of this is going to be two worked examples. So the first one will be getting some bright stars from the Gaia source catalog and playing around with those a little bit. And the second one will be attempting to identify some members of a cluster, M44, which is kind of resembles an introductory tutorial that I do, but we'll go a bit deeper into it and try and do some reproducible description of what that cluster looks like. We'll see as we go along. So this is sort of a assuming that you know some of the basics of what TOPCAT is and how it works. But if you don't, I'll try and kind of talk through all the steps that I'm doing. So hopefully, even if you haven't come across it before, you'll be able to work out what's going on. So I'm not going to be presenting slides. This will all be just a kind of hands-on demonstration. And I'll probably be running through it too quick for you to follow along and do the same thing at home, unless you're kind of pausing the video from time to time. But you can try and do that if you want. That's fine. That's recording good. So if you want to try and follow along, you can, but I may be going a bit too fast for you to do that. As far as questions go, I've got no objection to taking questions as we go along, but I don't know whether that's going to work given how people are connected. So if Priya wants to interrupt and say there's a question, that's fine, and I'm happy to answer it. Okay, let's go. So I'll start up TOPCAT. And the first thing that I'm going to do is to get some look at the Gaia source catalog and find the brightest stars in the sky. So the nominally visible stars, ones down to magnitude 6. And a good way to do that to get data in the first place, I'm going to be using the Gaia catalog, is to use TAP. So TAP is the table access protocol. From TOPCAT, I can get to TAP services by clicking this button here. And that takes me to the TAP window. And TAP, hopefully you've come across it already, but it's a way of posing database queries using an SQL-like language to a remote data service. And so the first thing TOPCAT does is show you a list of all the TAP servers out there. In this case, we're going to use this one, the Gaia service at ESA in Madrid. So I select that, choose use service, and then it goes off to Madrid and finds all the metadata of the tables that it's got. So it shows me the tables that we have. And in this case, I'm going to be interested in these are known as schemas. They're just like collections of tables. And in this case, what I'm interested in is the most recent Gaia data release, Gaia DR3. And here you can see all the tables that there are. I'll just go through this window a little bit because there's quite a lot going on. So in this case, we're interested in the Gaia source catalog of Gaia DR3, which is listed at the top here. If there's, in Gaia DR3, there's lots of tables, and you can just scroll up and down to try and find them, or you can list them alphabetically. By default, the service might list them in kind of the most interesting ones first. So you can do that, and then you can search for things in the name or in the description of the table as well. But in this case, Gaia source is the one we're after. And when I select that there, it shows me on this side a list of all the columns in that table. There's other tabs along here that tell me different things. So if I click on the table tab, it shows.
Could you zoom?
I'm sorry.
Could you
Is that
zoom?
too? Are you saying that's too small?
Yes. Yes.
That's a little tricky. I don't think I can very easily. So is that really too small to see what's going on?
Or just increase the window.
Um, yeah, I don't think I can do that on the screen that I've got. Let me see if there's something I can do. Um, is that better? Can you still see it?
It's fine. Better.
Is that better? Okay, and you can still see it. Right. Okay, so this is showing me information about a table. So it says what the table is. Maybe it says the number of rows in here. That's not always the case. It says it's got 1.8 billion rows. And there's a few other things as well in here. So this ADQL is the language that you use to talk to the remote database. And not all ADQLs are exactly the same. Different services have got different sets of functions and so on that are available. And so, for instance, in here, it gives me a list of the service-specific user-defined functions. And so these are functions that I can use when I'm making queries specifically to this service. So for instance, there's some sort of epoch propagation function here. And if I click on that, it tells me what they are. So you can investigate the way the TAP server works in quite a few ways. And finally, there's this hints tab over here, which gives you just a kind of very simple cheat sheet about how to use ADQL. Tells you what the structure of the select command is, which we're going to use down here. And points to a few other cheat sheets that you can look at as well. So if you've kind of forgotten how to use ADQL or you need a quick start, that's kind of a good place to look. But the main useful thing is this list here of all the columns. And you can see there's quite a lot. There's 100 and something columns in Gaia DR3. And you might know which ones you want, or you might be trying to find which ones you're after, which can be a bit tricky with all those columns there. So there's a couple of good tricks that you can use to find them. And if I click on one of these headings up here, so if I click on name, then these columns will get listed alphabetically by name. So if I know I'm looking for photometry, something, I can go down to P and find PHOT ones. Or if I click on the unit heading, I can find these listed alphabetically by unit. So if I don't even know what the column I'm after is, but I know it's got units of proper motion, then I can go down and look for something like milliarc seconds per year. And there we are. So these are all the proper motion like columns. So those are a couple of good ways to navigate around this list of columns. And if I click a couple more times, it'll go back to the natural order. Okay, so let's make the query that we're going to make. What I want to do is get all the sources with some useful information for them with magnitude less than 6, G magnitude less than 6. So I'm going to write select. I don't want all the columns because that'd be too many. I mean, I could ask for all the columns, but it would just mean getting more bytes than I have to. So I'll just pick a selection here. So I'm selecting all the columns that I'm interested in there, the astrometry and this one, FOTG mean mag, which is the G magnitude from this Gaia source catalog, where FOTG mean mag is less than 6. So all the sources with magnitude less than 6. And by the way, when I'm typing these, you can see that if I make a mistake, it'll highlight it because it can tell there's something wrong in the ADQL. If I click on this exclamation mark button here, then it'll give me some sort of error message, giving me a clue what might be wrong. But if you've got no red in there, then that's a good sign. So then I just hit run query, and it should go off and quite quickly gives me an answer. There are 6,000 rows there, so I can plot those on the sky by clicking the sky plot button here. So the next thing I might want to do, well, let's look at the table that I've got. So I've got the astrometry here. I've got a source ID, which is only makes any sense if you know what Gaia source IDs. It might be useful to have the names of these stars as well. So what I'm going to do is cross-match against Simbad. Simbad is a service run by CDS in Strasbourg, which has information about lots of sources in the galaxy and some extragalactic ones as well. And it knows things like their names, as well as aggregated information like magnitudes from and proper motions from various different surveys. But for this purpose, we just want to find the names of some of these sources. So I can do a cross match of this table with Simbad by clicking this button. That's the CDS cross match button, and that lets me take a table that I've loaded into TOPCAT, send it to a service in Strasbourg, which will match actually against any CDS table, any table in Visia, which is pretty much any astronomical table, small ones and big ones. And this is a list of some of the ones that it'll do, so 2MASS and Gaia and all sorts of things. But today I want to match against Simbad. Input table is the one that I've just loaded here. It fills in the RAN deck. Let's have radius within about 10 arc seconds and just hit go. So then that sends my table to Strasbourg, gets the result back, and it adds some more columns to it. So if I now look at the list of columns in the table, I've got all these columns, which are the ones that are requested from the Gaia tap service, and then all these ones which Simbad has added on. I don't want all of those because it's a bit too many to keep track of. So this is the list of all the columns that we've got. What I'm going to do is restrict the number of columns that we've got listed here by clicking and unclicking these things here. So if I click this button, it hides all of these columns, and then in the browser there's none of them shown, and I can just bring back the ones that I want. So let's just bring back the first 9 columns. And there we go. So now we've got this extra column from Simbad alongside the astrometry, which gives the name of each of those stars. Now I've got those names. I can plot them on the sky plot that I've done. I can do that by clicking on this form button, and this lets me do, so by default, I just get like a little spot for each of the points that I'm plotting, but I can do lots of other things as well. And one of the things that I can do, if I click on this forms, I get this list of different ways I can plot data as well. And this one, add label, adds a new item in this stack here. And I can choose for label, oh, I've got the wrong table. Problem here is I'm looking at the table before I'd done the Simbad match. Let's do it after I've done the Simbad match. Here we go. So there we go. Now we've got the main ID. And so then if I zoom in, I can see each of these stars, each of these spots is labeled with the Simbad identifier that it's got as well. So that's useful. Another thing that I might want to do is color code these stars according to their brightness. Let's turn off the labels for now. And again, I can do that using this Forms tab. So by default, where it's plotted spots on the sky, it does them using what's known as auto shading, which is it basically just looks like it plots them in one color. But if there's lots piled up on top of each other, then they go darker. But there's other options for that, and I'm going to use weighted here, which means it takes each of these spots and codes them by another quantity. In this case, we're going to choose the magnitude FOTG mean mag. So now the ones, let's make those a bit bigger. Now the darker spots are the ones with higher magnitude, the dimmer ones, and the lighter spots are the ones with lower magnitude. I'm going to fiddle around with the color map here a little bit. So if I go to this aux axis tab, I'll change this color map to Viridis, and I'm going to flip it so it goes the other way around. So it will now be the dark points are the ones that are brightest. So now you can see which points are brightest, which stars are brightest, and which stars are dimmest. Right, there's still quite a lot there. So what I'm going to do is try and cut these down to make it, well, just to make the plot a bit less crowded. Let's get rid of this window. And I can do that by making a subset of these. So I go to this subset window here. And this lists all the different row selections that I've got defined for this table at the moment. These two are just automatic ones, but I'm going to add a new one, which I'll call bright. And then I get to add an algebraic expression here. So what I can use is variables, which are the columns in the table, and then some expression in the syntax, which is actually Java syntax, but it's quite like, the sort of syntax you'd expect from any programming language. So if I write for gmeanmag is less than 4, it defines a new subset here. So there's only 600 of the 6,000. At the moment, it's plotting both the subsets. It's plotting all and the bright ones as well. So what I need to go is to go to this subsets tab and turn off all and just have the bright ones. So then these are just those sources which are, let's have the text labels back on. These are just the sources which are brighter than magnitude 4, and I can change that. And if I change it again, then now I've got only the ones which are brighter than magnitude 3. So that's useful, but it might be nice to be able to change this value kind of more fluidly than just typing in things there. So what I'm going to do is define what's known as a global variable and use that to define this cut. This is a newish feature of TOPCAT, so if you've been using it for a while, you might not have come across it. And I use this button here, Control Global Variables. And this gives me a window which lets me use a slider to change a variable that I can use in the expression language where I'm defining subsets or defining other columns or whatever it is. So by default, this one var $x goes from 0 to 1. I want to change it so it goes from 0 to 6. So let's change that to 6 there. And then I can use that in this expression. I double click in here to change the expression. I do var.x. And so then when I change the slider, then I can bring in more or less of these stars according to brightness as I want. So that can be quite a useful way using these global variables of adjusting the display on the fly. All right, another thing that might be nice if we're looking at the sky is to look at what constellations these sources are in. Actually, I'm going to change the way that this plot is done. So at the moment, this is a sign projection, so it looks like a sphere. I'm going to go to this axes tab and change it so we get an all sky projection. So I'm going to change this projection here from sign to ITOF. And then we get a familiar ITOF projection here. And other things I can do, I can change it to galactic coordinates, a galactic projection if I want to, but let's keep it equatorial. All right, so I want to know which constellation these things are in. Now, TOPCAT doesn't know anything about constellations. Actually, it doesn't know all that much about astronomy, but it can talk to services which do. So if I go back to the TAP service, to the TAP window, I'm going to do a search for TAP services which know something about constellations. So I'll just type in constellation. And it gives me a couple of services here. There's Visio, which has got various ones, but the one I'm going to use is this one, GavoDC, which is a service in Heidelberg. It's very useful. It's got lots of information, lots of interesting data in there. And it's got this table, cstl.go. So we do use service, and then we can query that table. And here we are, we've got this, this table here. It's found for us. And it's just got a few columns. It's got constellation name and abbreviation. some definition of the shape of that constellation and a central RN deck. So since it's a list of constellations, it's probably not going to be very long. I can just download the whole table, which I do using select star from cstl.go. And if I look at that, I can see what that table looked like. So it's got the abbreviations and the names of the constellation, and then this thing, which is presumably some sort of list of vertices defining the shape of the constellation and a central RN deck. So now I'm going to overplot that on the sky. Where's my sky plot gone? There it is. Normally, if I want to overplot another set of data on the data that I've got, I'd click this button here, and then that would give me, well, I'll try it. That gives me the chance to enter another table and new latitude and longitude positions, and then that would overplot another set of points on top of what I've got. But in this case, I don't want a set of points. What I want is a set of shapes. And so I'm going to click this button here. So these give you different kinds of plots that you can do. So I'm going to hit this one, which is shapes. The tooltip says add a new area plot control to the stack. So it does that. And choose the table that I've just downloaded, the constellations one. And then it knows enough that it can identify this column P as the shape, and you can see the shapes of the constellations have been overplotted on here. And again, if I go to the Form tab, I can do different kinds of plots based on that shape. So in this case, I'll add this text label to the constellations as well. And I can choose name. So now I can see this is where Cetus is, and Fornax and Sculptor, and so it's labeled all the constellations for me. Let's bring back a few more of the sources. Okay, so that's good so far. And I'm going to do one more thing with this set of data, which is see how these sources are moving, see how these stars are moving in proper motion across the sky as time goes on. So Gaia gives us very accurate proper motions. And so we can use that to calculate where these things are going to be in 1,000 or 10,000 years' time. To do that, we're going to be adding a new column to our table here. And that column is going to have the position that these objects will be in some time in the future. So to do that, I need to write an expression which will give that position. And for that, I need to use the expression language. If I click this button with the FX up on the top there, it gives me a list of all the special functions that are available in that expression language. And there's all sorts of things there. There's arithmetic ones like maximum and minimum. There are ones for converting time values, and you can search for these in the manual, but the ones we're going to use today are in this Gaia category. And there's various things here, but one of them that is there is this epoch prop function. So that propagates the position from one epoch to another. And this one's it's designed to be easy to use for Gaia data because that's often the data that you're going to be using if you're doing proper motions. And over here it explains exactly what it does and the syntax and so on. And if I go down to the bottom, I can kind of cheat. And this is an example. And so this is how you'd use it. You use epoch prop and then the number of years in the future or past that you want to have the positions in. And then this expression array with the RA index and parallax and so on, so that it takes those values and calculates a position at some time.
Sorry, not all your windows are shown.
Oh, really?
Yeah.
No, you're right.
The ones where you type it.
I think this is to do with me changing the zoom. All right, let me try and leave Zoom and come back again.
No, it's okay. It's okay.
Well, no, because otherwise you can't see what's going on.
It's fine now.
Let me just. It's not because I can monitor on another screen and you can't see the same windows that I can see. I'll just leave and come back again and see if that helps, or at least I'll unshare anyway. See if that helps. Now I can't even find Zoom. It's a bad sign. Um, okay, I'm back. Can you allow me to share my screen again? Can I share my screen? Can you hear me? Thank you. Okay, can you see my screen? Can you hear me?
Yes.
All right, sorry about that. Okay, I think that's better. Yeah, okay. So this is what you should have been seeing just now. So this explains how you can use the function that you can use to do the epoch propagation. So we'll go back to the columns window and add a new column, which I do using this green plus button. So I'll call this future pos for future position, and the expression is going to be, which I've just copied from that documentation there. We'll see what it looks like 100,000 years into the future. Um, so it's added this new column, future pos. If I go and look at that column in the table, I can see it's an array. And if you look at the documentation again, the first two quantities are RA and DEC in the future, and then that's the parallax in the future and so on. So I can plot those on this window as well. And again, what I'm not, I could just plot the future positions by using this button here, which would give me the another overplotted set of points. But what I'm going to do is plot this button here, use this button here, which lets me plot pairs of points with lines between them. So I'll choose that table, and the first pair of position, sorry, the first position will be RN deck, which is my original positions, and then I'll use future pos, and I use these square brackets to pick out elements of the array. So the first two elements of the array are the RN deck of the future position. If I do that, I can see these little lines which show me where the originally source is and where it'll be in 10,000 years time. Let me refine that a bit. So if I go to the subsets window, I'll just look at those for the bright sources so I don't get them all. Let's have a few more bright sources, up to about magnitude 4 maybe. And I'll change the form. So by default, it just does a little line here, but let's fix it so that I get circles at both ends as well. Hollow circles and make them a bit bigger. Let's turn off the text. And so then you can see for these sources, they're going to go from there to there in the next 10,000 years. And now I can do a similar trick with the global variables. So I'll define a time variable. I'll call that var $t. I'm using a different one. And I'll take that to go from 0 to 100,000 years in the future. And then I can change the expression in the column definition. Here's the expression, and I can just double click on that and edit it. And so instead of that fixed 100,000, I'll have var $t in there. And then when I move this, it will change continuously the distances that those are going. There's a little complication here, which is if I zoom in and then change this value again, it will redo the auto zoom. So what I need to do in order to stop that happening is click on this button here with the lock and the axes, and that locks the axes and doesn't auto zoom when I don't ask it to. So then I can zoom in and use this slider, and then the thing won't rescale itself while I do it. So there you can see how those things are moving, what those constellations are going to look like in 100,000 years' time. Okay, so that's the end of the first example. It covered quite a lot. So we've had how to make selections, various uses of the expression language, using the TAP service, using the CDS cross-match service, these global variables with the sliders, and quite a few different plot options. If there's any questions at that stage, I'm happy to answer them. But if not, or if the questions aren't really working in this format, that's fine. I can just go on to the next one. I'll take the time to clear up some of these windows. Okay, so I'll go to the second example. So what we're doing in this one is looking at members of a cluster. And if you've seen a TOPCAT demonstration before, you'll quite likely have seen something like this, where we get some sources in one part of the sky. We're going to be using Gaia data again, where we expect to find some cluster members, and then look at where they sit in proper motion space and identify from that which are the real cluster members and which are background sources, and then do some analysis on that basis. So we're going to do that now, but with a bit more detail. And in particular, we're going to try and do it so that we can define later reproducibly what the selection of sources that we've got is. So to find cluster sources, if we're looking at a particular part of the sky, a good place to start is a cone search. So we do that from this VO window, VO menu up here. I'll click cone search, and this lets me go to a particular service which has got cone search data, and and request all the sources from those catalogs in a particular part of the sky. We're going to get Gaia data again, so I'll search for Gaia DR3, and as you can see, there's lots of cone search services here, and I could pick many of them and they'd give me similar results, but I'm going to go for this one, ARI Gaia, which is a service in Heidelberg. So that defines which of these services I'm going to be using. We're going to be looking at M44, so I type M44 in here and hit return, and then that goes off again to Simbad and finds out what the sky position of M44 is and fills it in here. And we're going to look at about 1.5 degrees around that position. I could just hit go now and it would go and get them. I'm going to change this verbosity selector to minimum. All that does is change the number of columns you get back, and it just because we don't need lots and lots of the data, we just need the basic stuff. I'm going to put it to minimum. If you didn't do that, you just get more columns than you maybe needed. So hit OK. And that should go off and bring me back some sources in the area of the sky that I asked for. So the first thing to do is plot it on the sky, and it looks like that. That's what we expected. I asked for a cone. I got a cone. There's 40,000 sources there, and some of these will be in M44, but many of them will be background sources. So the next thing that I'll do, as usual, is to do a plot in proper motion space instead. So I do a plane plot now instead of a sky plot. And I'm going to plot in proper motion in RA versus proper motion in declination. And you can see there are these two very distinct subpopulations. This is the background sources, and these ones in the same region of proper motion space are co-moving across the sky. So these are the ones that are actually cluster members. They're associated with each other in phase space and also presumably in kind of composition and formation time and so on. So the first thing I'm going to do is draw a blob around these to identify them as a particular set. And I just click on that button up there and draw a blob like that and click again. And that identifies these, and I'll call those cluster. And then you can see it's pointed these in blue, and it's defined a new subset just based on those, which I can plot on its own if I want to. And it's done the same thing over on the sky plot as well. So you can see in blue, these are the sources that are probably in the cluster itself, and the red ones are background ones. And I can, again, turn off the background ones. So these are really just the sources we're interested in. I can now do an HR diagram as well. So I'll do another plane plot here. And we should have BP minus RP color. There we go. Versus G magnitude for G mean mag. So that's an HR diagram of all the sources that we asked for. It's upside down, so I can go to the axes control here and do this click Y flip, and that will just turn the Y axis so it goes from higher values to lower values, dimmer to brighter rather than the other way around. I can do other changes to the axes here as well. So for instance, if I wanted this to be a logarithmic axis, I could do that. We don't need it because it already is logarithmic, but that's how you do those controls. And then I go back to the subsets tab and highlight the cluster ones, and you can see the cluster are on a nice tight main sequence, whereas the background objects are all over the place, and that's because the cluster ones are formed at the same time, and they're also at the same distance. So the observed magnitude, the apparent magnitude, is a good proxy for absolute magnitude. We can turn off the background sources. So this already looks quite good. You can see this is most of the main sequence. There's a giant branch up here, and here are some white dwarfs. But there's also definitely some outliers here. And what that is presumably some of the sources that I've identified here just happen to be in the right region of proper motion space. They're not really in this cluster at all. They're associated with the background. So there's a few ways that I can refine that. First thing I'm going to do is look at the parallax. Excuse me. So I can do a histogram of the parallax. That's histogram plot. I just click on this button here. And that's parallax of all the sources. Again, go to the subsets tab and just do histogram of the cluster sources. If I click one of these buttons up here, it'll rescale so I can see what's going on better. And you can see they're fairly tightly bunched between sort of 4 and 6, but there's these outliers here. So these ones with very different parallax to the rest of the cluster are presumably not part of the cluster at all, and we should throw them out. So I'd say this is probably between about 4.6 and 6. Looks like most of the ones in the cluster, and we can get rid of the other ones. So I can define a new subset just based on those. We'll go back to the subsets window here, and we'll refine what we've got here. So we've already got this cluster subset. Those are the ones we're interested in. Add a new subset here. which I'll call cluster 2. And so this expression is going to be only ones which are in the original cluster selection. And parallax is greater than, what did I say, 4.6, and parallax is less than 6. So the syntax I've got here, I've used this ampersand, ampersand, and that's just the syntax that you need for ands in this expression language. That's Java syntax, but it's the same as you'd get from C syntax. It's different than what you get in Python, but you just have to remember that's how you do ands in Java. And in TOPCAT's expression language. For ORs, use a pipe character doubled again. So we can do that, and then we've refined our subset. And so now this green one is cluster 2, and you can see it's only in this region of parallax space. If I go back to the HR diagram, you can see these green ones are still in the selection, and it's thrown out a lot of these blue ones. So that's what we were hoping. The ones in the wrong region of parallax space are also in the wrong region of color magnitude space. And so we've already got, if we turn off those blue ones, a cleaner selection. There's still some that are probably not on this cluster properly. There's these ones down here, and there's some of these ones kind of above the main part of the main sequence. So one of the quantities that we get from Gaia data is this value RUA, renormalized unit weight error. I'm not going to go in detail into what that means, but it's a sort of proxy for how good the astrometric fit is. And so essentially, if you get large values of that column, then the quantities that you're looking at are going to be less reliable than if you get small values of that quantity. So what we want to do is restrict, or at least play around with restricting the points that we've plotted to only the ones with a small value of RUA. But what's small enough? So what I'll do is, again, I'll plot these points, let's make it a bit bigger, plot these points color coded by the value of that quantity. So I use, again, this weighted shading mode. And you can see some of the darker ones are indeed sat off this main sequence, so we should probably exclude those. And let's fiddle around a little bit with this, with the color coding. So I can go to aux axis. I'm going to change the range. So let's compress this a bit so that we can see more what's going on at the lower range of this. And then you can see, so many of these dark ones something between probably about 1 and 4 we should get rid of. What I'm going to do is, again, use this global variable to refine which values of RUA we're going to use. So we go back to the cluster definition. And let's define a new global variable here to act as a threshold for RUA thresholding. So I'll call that var $R, and let's say it goes between 0 and 5. So that slider can go between 0 and 5. And then I'll add a new condition on here, and RUA is less than var $R, so less than this quantity down here. So then I can change this slider, and actually I'm going to lock the. I'm just going to lock the color map there. So now I can play around with this slider, and by reducing this, I can see when it gets, if it's too low, then I throw out all the values. If it's too high, then I leave in too many of the bad ones. So I can just slide it down to a stage where it has a balance between throwing out the least good ones, the least good fits, but not getting rid of all the good fits. And I would say that's somewhere about, I don't know, depends what you want to do, but maybe there. So that's a value of about 1.4. So then I can substitute that back in here. Now I've finished doing my experimentation, and I've got RUA less than 1.4. Okay, so that's now, I mean, you could do some additional work here. You could throw out these ones here by doing another blob and combining that quantity with the selections that we've already got. But let's say this is the selection that we want to use. So now we can do some science on that cluster, whatever it is, and we've got a reasonable selection of sources to do it on. So that's good, but suppose what you now want to do is do your science and then write a paper on it and publish the paper. What it would be really good to be able to do is say, write in the paper, okay, this is exactly how I acquired these sources, and then that science becomes reproducible, and someone else can do exactly the same query on the Gaia source catalog and get the same sources back and see exactly what you're doing and reproduce your work. So what we want to do is come up with a tap query which corresponds to pulling out this selection of sources from the Gaia source catalog. So let's go to the Gaia source catalog in tab. We're back in Gaia again. This is the standard service at ESAC. We're using the Gaia source catalog again. So what we need to do is reproduce in ADQL all the steps that we took in order to make that selection. I went through this way. I'll push this button here, and then that gives me another pane that I can write a new query in. So you can have multiple ones of these on the go at the same time. So the first thing that we did was select by sky position, and we did this cone search query. Oops, to do that. Did this cone search query here. So we want to reproduce the cone search query in ADQL. If you can't remember how to do that, that's okay. A good place to start is using this examples menu here. So if I click examples, and this is a useful menu to use anyway. It tells you just kind of basic examples of how you can use tap services. So if you want to do a basic query, it looks like that. If you want to do a box selection, it looks like that. And depending on what service you're looking at, there might be some service provided ones as well. So in this case, these are queries provided by the Gaia service itself. And so if you want to find cone search in galactic coordinates, you can try this and it will show you roughly what a query like that looks like. And you won't just use that as it is, but you can use it as a basis for editing that ADQL. And then you can come up with the query that you actually want. So in this case, we're going to look at the cone selection one. And so this is basically what it looks like. Select something from whatever table you want. And this is the important bit where distance, RA dec, and then your actual sky position is less than some distance in degrees. So let's adapt it for our purposes. The columns we wanted were, let's have source, ID, RA dec, PM, PM, RA, PM dec. BP minus RP and FOP G mean mag. Oh, let's have radial velocity. Okay, so select those columns from, that's the right table, where the distance, so the cone search that we had was here. So these are the coordinates that we want to use. So copy them from there into here. And it's less than 1.5 degrees. So that takes care of the distance. The next thing that we did was look at the position in proper motion space. So here we are. Now this is a bit trickier because what we did was draw a blob around this part of the sky, and you can't easily turn that into something in ADQL. We did that by clicking this button, which lets us play around with the mouse. But another way of doing a graphical selection exists, and that's this button next to it. So this does the same sort of thing, but instead of doing free-form selection with the mouse, it gives you a set of geometrical shapes which have got well-defined algebraic properties to them. So there's various options here. I can choose circle in this case to keep it simple. So what I can do now is try and identify about the same selection that I had before, but so I've chosen that. I click on it once and then draw out the mouse to about where I want to take it to and click on it again, and then go back up here. And so when I've done that, I can define a new subset based on this circle rather than doing it via the blob. But the other useful thing that this tells me is an ADQL expression corresponding to exactly what I've written here. So what I can do is cut and paste this into the tap window.
replan है क्या वही वाला अभी
and I think there's someone else's microphone open, unless someone's asking me a question. I'll try and plow on. So then I've got that ADQL expression. It's put X and Y in here, but what I actually want is the X and Y coordinates of this plot, which are proper motion in RA and proper motion in DEC. So I can do PM RA in there and PM DEC in there. So this is now the condition which defines the region in proper motion space that I'd defined graphically before. And the other things that I'd put in there were in the subsets window. These are already algebraic expressions about the parallax and the Rua. So I can just paste those into here. Oops, I need an and. If I look here, I've got this warning thing lit up, and that's because I've got the wrong syntax for ands here. So the ands that I used in TOPCAT's expression language are not the same as the ands that I use in ADQL. So I just need to change that and to that and that and to that and. And so what we've got now here is a query which does exactly the same, nearly exactly the same as the queries that we worked through using the GUI of TOPCAT to refine that HR diagram. So if I click run query, it should go off, submit this to the TAP service in Madrid, and bring me back exactly the sources that I wanted. And I can take this ADQL and write it in my paper in an appendix or in the text and say this is exactly the sources that I was after. One thing that's worth knowing when you're using the virtual observatory, TAP services and things like that is it doesn't always run completely smoothly. There are things that don't work quite as you like to. There's a few kind of kinks. One of the things about this one is, and I only found this out by trial and error, if I write this query like this, it actually takes quite a long time to execute. It will come back eventually, but it turns out it's quicker when you're talking to this particular TAP service. If instead of writing distance RA DEC and then the fixed position, you write distance fixed position and then RA DEC, which means exactly the same thing, but the way that the SQL engine executes it takes a different amount of time. So, okay, it's timed out. I could fix it so that it had longer to run, but instead I'm just going to rewrite this the other way around with exactly the same semantics. So if I do that, it runs almost immediately. And that's the table that I've got back without any kind of direct graphical intervention. And I should be able to do the HR diagram directly just from those sources. So there we are. That's the nice clean HR diagram using this selection. So that's reproducible selections, and it works nicely. So that's close to the end of the hour. I could say a little bit about cluster dynamics and calculating positions and velocities within that cluster, or I could leave it there, and if there's any questions, I could answer them now. That might be best. Priya, do you have an opinion?
Please go ahead.
Okay. So we've now got these quantities, and we've got RA deck parallax, PMRA, PM deck, and radial velocities. So that's 6 quantities, which is enough to give us positions and motions in 6-dimensional phase space, but they're not in a very useful format for looking at 3-dimensional. We don't have 3-dimensional Cartesian components of those positions and velocities yet. So we can again use the expression language to convert these into those quantities. And again, if I look at the expression language browser there, it's one of these functions in the Gaia section. So Astrom XYZ takes RA deck and parallax and turns them into positions in 3 dimensions, 3 Cartesian dimensions. And this one, Astrom UVW, takes those quantities and turns them into velocities, 3-component velocities. So let's add those in the columns window. We use this plus button. So XYZ is Astrom XYZ RA deck parallax. I think that's in parsec. If you read the documentation, it will tell you. And then velocities, I can do UVW. I think that's in kilometers a second. Okay, so if we now look at the table, you can see it's added these 2 additional columns. Each of those is a 3-vector. That's position, and this is velocity. Some of these are nans because radial velocity isn't observed for all the sources, but the ones we've got them, it's given us velocities. So we can plot those in 3 dimensions using this this cube plotting button. And I could write XYZ square brackets 0, 1, 2 in this XYZ column field entries here, but I'm going to use this vector choice instead, which lets me plot a 3-vector directly. So these are the positions in real space. Almost. So by default, it rescales this cube to fit these things in with not necessarily the same scales on each of these axes. But if I go to the axes, control and push isometric, then this is in an isometric view. So all the distances are what they look like. And I'll just change the plotting on that a little bit. So that's what these things actually look like in 3D positions. They're elongated in one line because the radial velocity determinations done by Gaia are not as accurate as the proper motion determination. So these ones are better constrained than these ones. And then I can plot the velocities on top of those. Again, I do it using this forms button here, and I can go down to add XYZ vector. And so here I can use those UVW values that I had calculated. So now I have the velocities for all those things. Unsurprisingly, they're all pointing in more or less the same direction. Because the cluster's moving in more or less the same direction. What might be nice would be to work out kind of relative velocities so that I can see how those things are moving within the cluster. There's not a really straightforward way to do that, but I can do it. So if I look at this button here, it gives me statistics on the columns of the table. And it gives me mean and standard deviations of these things. It hasn't given me a mean for the velocity because this is a vector and it only does scalar quantities up here, but I can get it to do that. If I click on the display menu up here, it gives me lots of other statistical quantities that it will calculate for me if I like. And what I want here is array means. So if I regenerate that, oh, sorry, there we are. So the mean value of this UVW is that. in kilometers a second. So I can then subtract those mean values from what I've calculated here. So it's that one minus 1.4128 minus 47.26 minus 0.637. So then what I've got here is the relative, let's turn off the spots, is the relative motions of those objects within that cluster. Does it tell us anything very interesting? Not much. You can't see much in the way of a kind of swirly motion or anything like that. But if there was one, then maybe you'd be able to see it there. And you can scale the size of those arrows, so it makes it easier to see what's going on as well. Okay, that's very nearly the hour, so I will stop there. Thanks very much for your attention. If it's feasible to ask questions, I'm happy to, but otherwise, thanks very much for listening. I would try and unshare my screen, but I'm not sure how to do it.
I'm scared to speak. So thanks a lot, Mark. Can you hear me? I think now we've sorted
thank
that
you.
problem. Now I can't hear you. Achha, now we can. Yeah. Okay. Yeah. So thanks a lot.
Okay, thanks very much.
Many useful things you said, which was especially useful for me. I really loved the talk. It was really very nice. Lots of new things in TOPCAT which need to be explored. I think people are overwhelmed, but I'm thrilled.
Yeah, probably
I'm
so.
happy. So thank you so much. Yeah. Thanks a lot.
Thanks a lot.
Yeah.
Thank you.
Thank you so much. Bye-bye.
I'm trying to
We'll follow
unshare
up
my
on
screen,
your
but I can't, so
lecture
please
and-
do it for me.
Continue with the students.
Yeah. Okay, bye-bye.
Thank you.
Bye-bye.
Bye-bye. I don't know. Well, again. Okay. Yeah. So thank you. And bye-bye. Thanks. Okay. I think I should stop his live stream.